Hello, in this video I'm going to go over the test number 5 that was completed during the college algebra course in preparation for our final exam. For test number 5 it was all about polynomial and rational functions, and for this test our only objective was to start with an equation and determine its behavior, or in other words what its graph would look like without the use of a graphing calculator. So right off the bat with this first example here of a polynomial, we had to use the rational roots theorem to identify possible rational roots. So normally we would look for our constant at the end and call this our p-value, and our leading coefficient at the beginning and call that our q-value. But since p is 0 in this case, we actually have to do one preliminary step here, and that's to factor out a common factor of x. So I would call this x times negative x squared plus 3x minus 2. And now we can note that p is 2 and q is 1, and we can proceed from there. So then with our p-value of 2 and a q-value of 1, the possible factors of p are 1 and 2, the factors of q are 1, and when each of the factors of p are divided by each of the factors of q, we get the same list as p. But I do also want to include, let's also not forget that 0 is a possible root. In fact, it's a known root because of the factors that we see out here. So when we determine the rational roots, we need to evaluate this function at each of the possible roots. So at 1, at negative 1, at 2, and negative 2. We already know that f evaluated at 0 is going to equal 0. So I'll go ahead and put a box around that. Now you should recall that we can use a non-graphing calculator to evaluate the potential zeros. So I'm using my TI Inspire, or you can use the TI 30s like we have in the classroom, to type the function based on the letter A. The computer doesn't know what to do with that. The calculator doesn't know what to do with that at first. But if we take our potential zeros and store them, so in this case I'll press 1 and then control variable to call the store command. If I store that potential 0 as A, then when I highlight the prior expression and tap enter, this will recalculate the formula at that number, and in this case we do find a root at 1. So when x is 1, we do have a root, so there's one of my roots. And we'll do the same for negative 1, positive 2, and negative 2. So negative 1, store as A. Oops. Press enter first. Then I'll call the last equation. That one did not work, so we'll try 2. Store that as A. Oops. Store that as A. Call the last equation, and we get another 0. I can stop there because this was equal to 6, this was equal to 0. That's my third 0, and we also should recognize that from the beginning there are only 3 zeros after all, so there's no need to test this last one. So as far as reporting your answer, I was okay like this, but you can also say that the roots exist like this. We could say that there's one at 0, at 1, and at 2, and that would be a fine answer. So use the rational roots to factor the polynomial. Well, there's no need to use any division here. We found all of the roots, so the polynomial f of x would have to be written as x from this factor times x minus 1 from this factor times x minus 2 from that factor. So there's our factored polynomial. The y-intercept comes from our non-factored result, so the constant that was at the end of the expression originally was 0, so we have a y-intercept at 0, 0, and now we can sketch a graph of the polynomial. So I could cheat just a little bit since I'm using electronic ink, and there's my x-axis. We have an intercept on the y-axis here at 0, 0. That's also an x-intercept. We have an intercept at 1, 0 and 2, 0 as well. With a leading coefficient that's less than 0, a leading coefficient that's negative, that means my right side tail is pointing down, and with a degree that's odd, that means the opposite tail has to be pointing in the opposite direction. So this tail is going to be pointing up, and in order for us to have a smooth and continuous line to connect those, we'd have to sketch the rest of our graph that looks something like this. And I think that would be a pretty good solution for number 1. For the next example, I'm going to work through it a little bit more quickly here, and I'll pause the video while I'm recording so that we don't spend too much time talking about it. So in this example, we have a p-value of 4 and a q-value of 4, and their factors are listed here. Every factor of p, when divided by every factor of q, produces a distinct list of 1, 2, 4, 1/2, and 1/4. So that means that we could use our calculator and evaluate all 10 of these numbers, and we're hoping to find 4 solutions. I'll also note that if we find at least 2 of them, then we can use synthetic division to find the remaining rational roots. Let's see what happens when we start checking these. Now right off the bat, we get pretty lucky here. You'll notice that I wrote my equation with b's instead of a's this time. And when I checked the value of b at 1 and the value of b at -1, both of them came out to be zeros. Now that tells me that 2 of my zeros occur right here, but that also tells me that this is a good candidate for polynomial division, or in this case, synthetic division. I can reduce this from a 4th degree polynomial to a 2nd degree polynomial, and I personally find it a little bit faster to find my zeros that way. Let me show you what I mean. If I use 4, -15, -8, +15, and 4, I know that one of my known zeros is here at 1. Oops, and I made a mistake already, so maybe this wasn't faster after all. -15 and 4 made, oops, did it again. -15 plus 4 is -11. So -11 here is -19. -19 plus 15 is -4. -4, 0. There we go. So I use that first known zero and the second known zero. -19 and 15 is -4. -4 times -1 is +4. That's a 0. All right, so now what this leaves me with then is a quadratic that is represented by these coefficients, 4x squared minus 15x minus 4. And even though it's a non-standard trinomial, I'm going to guess that that's factorable. I'm going to go with 4x and x, and then I'm going to put 4 and 1 here. A -4, +1 is going to work. When this foils back together, we come back to this as the expression. So this now tells me that the other 0 has to occur at x equals -1/4 and when x is equal to +4. So there was no need for me to continue checking. We have 2 zeros that were found here, but by factoring and synthetic division, we ended up finding another 0 that would have occurred here at the very end, and then also here along the way. So, not everybody is going to use this technique, this synthetic division, in addition to our rational roots theorem, but for those of you that are comfortable with factoring, you just might do that. So 1, -1, 4, and -1/4 are our rational roots. Since we found them all, and since we've already gone through some of the factoring process, we should now recognize that f of x is equal to x plus 1 times x minus 1 times 4x plus 1 times x minus 4. So there's our factored result, and all of those came from the prior factors and the solutions that we found in the step above. The y-intercept is easy to spot. The y-intercept is the constant at the end of the original polynomial. So I'm going to report that as a coordinate, 0, 4. And as far as the sketch of the polynomial goes, We have a y-intercept at positive 4, an x-intercept at positive 1, negative 1, negative 1/4. Ooh, this is getting kind of tight here. Negative 1/4 and positive 4. We have a positive leading coefficient with an even degree, so that means the right tail has to point up and the left tail also points up. And in order to connect these with a smooth and continuous line, it might look something like this. I think this dip on the right-hand side is going to drop lower than the one on the left because of the distance between the x-intercepts. And I feel that that would be a pretty good sketch of the behavior of this graph. Now for our last polynomial to graph, we have a p-value of 4 and a q-value of 1. So the potential zeros here for p divided by q are just going to be the same as p. I know that much already. And the factors for p are positive and negative. Okay, they're going to be, let's see here if that starts working again. There we go. Positive and negative. I don't know why my ink stops working here. Let me try that again. Okay, one more try. Let's see if this is going to respond now. Positive and negative, 1, 2, and 4. Our q value is 1, so the factors of q are positive and negative 1. And we said a minute ago that p divided by q is going to be the same as our list of p, and it's the same because our q value is 1. All right, so our rational roots. Now, I've only got 6 to check, so this time I don't think I'll even bother trying to use the rational roots theorem or synthetic division to find these. I'll just use brute force and check all of them. So f evaluated at 1, negative 1, 2, negative 2, and f should be evaluated at 4 and negative 4. Now you'll notice again with this example, both 1 and negative 1 right off the bat produced zeros. So it's real tempting for me just to use synthetic division to finish this out, but I'm going to go ahead and check the rest of these 2, negative 2, 4, and negative 4. Now by checking 2 and negative 2, I see that 2 did not work, but negative 2 did. And let's see if we can find the last one between 4 and negative 4. So I'll store 4 as C and execute the equation. So 4 doesn't work. Let's check negative 4. Remember, there's no guarantee here. Something interesting would occur if this doesn't work. Let's take a look. Okay, so that didn't work either. So this is kind of interesting. The equation leads me to believe that there are 4 roots. There are 4 roots. And we found 3 rational roots. Now, the interesting thing about these roots is that they tend to come in pairs. We have 3 rational roots, and the 4th one, I'm guessing, is going to be some example of multiplicity here. It's impossible for us to have a non-real number answer if we found 3 real answers, but it's also unlikely for us to have 3 rational roots and 1 irrational root. I don't know if that's possible or not. I haven't looked into that very closely, but I'm wondering if there's multiplicity on one of these. So while I was hoping to avoid synthetic division in this case, I think we're going to have to, because if we want to finish factoring this completely, we have to find that 4th factor based on the 3 known factors. So let's see what happens. With synthetic division, we can start with 1, 4, 3, negative 4, and negative 4, and we're going to test all 3 of these known roots. So after our first root of positive 1, we ended up with a remainder of 0, which is a good sign. So we'll now reduce again using our second root that we found. And that looks good. We again have another remainder of 0. Now, I recognize that this represents x squared plus 4x plus 4, and I know a little bit about that trinomial, but let's go ahead and finish this out by synthetic division using the number 2, negative 2 here. So this adds to 1, multiplies to make negative 2, adds to equal 2, and that multiplies to make negative 4. So again, we've got a remainder of 0. None of that should be a surprise, but what this does tell me is that we finished, after factoring, with one more factor at x plus 2. Right? This result down here is an x plus 2. We had started with an x to the 4th equation, reduced to x to the 3rd, x squared, so now finally x plus 2. So from this from that 0, and that 0, we knew that the factors were going to be x minus 1, then x plus 1, and then x plus 2, because these factors are the opposite of the zeros that we were checking. And then we found another x plus 2 right here, and as I had suspected, there is multiplicity after all. F of x is equal to x minus 1 times x plus 1 times x plus 2 quantity squared. We have the multiplicity at that 0. So when we talk about our y-intercept, that's going to occur at negative 4. 0, negative 4. We should have enough information for us to sketch a graph at this point. We have a y-intercept at negative 4. We have a 0 at negative 2, a 0 at negative 1, and a 0 at positive 1. Because this is a positive leading coefficient with an even degree, we know both tails are pointing up in this case. And because of the multiplicity at this 0, I know that the graph is going to touch this x-axis and turn away. That means that it's going to have to turn back down and go through the x-axis at negative 1. It'll strike the y-axis at negative 4, and it'll turn back up to go through the x-axis at positive 1. And I think that would be a pretty good sketch for this particular function. Now that completes our polynomial portion of the test. Let's move on down to the rational function portion of the test. We always start by factoring first, and it looks like the denominator can be factored, but that's it. So now if I start my analysis, the horizontal asymptote, well, the numerator degree is 0, the denominator degree is 2, so this guy is smaller than this one, so that tells me my horizontal asymptote has to be at y equals 0. As far as our vertical asymptotes go, that exists when there's a non-removable discontinuity, so that appears to happen at x equals 0, and when x is equal to negative 3. There won't be any slanted asymptotes or anything else, so we've now found all of the asymptotes. There are no holes in this case because there are no removable discontinuities. So let's talk about x-intercepts. Now this is going to be kind of interesting because we have a horizontal asymptote at y equals 0. There might not be any x-intercepts. If we were to find any x-intercepts, those would occur when y is equal to 0. And if we were to set the equation equal to 0, we only have to worry about the numerator. When does 0 equal negative 4? Well, that's not possible. 0 does not equal negative 4, so there are no x-intercepts. For y-intercepts, I think we're going to be in the same position here. Y-intercepts are found when x is equal to 0, but we've got a problem there. We can't let x be equal to 0 because negative 4 divided by 0 is undefined. There are no y-intercepts either. So we're kind of out of luck as far as the graph goes. We need some test points. I think a good test point to check would be some number to the left of this asymptote. So I might choose a test point of negative 4. I think a test point really close to this asymptote and close to this one might be good. So I might test at f evaluated at negative 3.9. Sorry, negative 2.9. And then I might test at negative 0.1. That's really close to 0. And then we'll go ahead and pick another test point. A little bit further to the right is okay. We'll choose a test point of 1. So 4 test points look like they'd be necessary here for us to determine the behavior of the graph. We might be able to get away with just 3, because I know there are no x-intercepts in the center here. I'm guessing that there's going to be a U-shaped graph somewhere in the middle, and we could spot that with just a single test point. But I'll use 2 just to be safe. And so off camera I used a calculator, much the same way that we were evaluating the polynomials, and I found these 4 results. When x was equal to -4, we had a y coordinate of -1. So that tells me we've got a coordinate down here. That leads me to believe that the graph is going to be bounded by the horizontal and vertical asymptotes like this. When x is equal to -2.9, we ended up having a y coordinate of +13.8, and same thing happened at -0.1. So those 2 coordinates were way up off the screen. That leads me to believe that we've got an upward turning U shape here in the middle. I don't know the exact shape of it, but I think it's going to look something like this. I know that it's not going to snake across because there were no x-intercepts in between, so I'm fairly confident that it's bounded in the upper region here. And then lastly, when x is +1, we get a y value of -1 as well. So that tells me that this is going to be bounded down here horizontally and vertically, and I'm guessing that this is going to be a pretty good shape. And I would be satisfied if you can reproduce this on your test. Let's go on to the last example then. All right, so here we are again with our last example. Again, the first thing that I like to do is factor everything first. So in its factored form, we might have something like this, and we'll also note that these factors x will remove themselves. So we now have x minus 2 times x minus 4 over negative x minus 3. So that's a removable discontinuity. We're going to create a hole there. Let's go ahead and find that. There's a hole in the graph when x is equal to 0. Now, if I were to change x to 0, I'd have -2 times -4, which is -8, over -0 minus 3, which is -3. So that's -8 thirds. So we have a hole at -8 thirds. Because there's a non-removable discontinuity here, then I know that there's a vertical asymptote at x equals 3. Because this degree is larger than this degree by 1, I know there's no horizontal asymptote, but apparently there's going to be a slanted asymptote. So if I take the equation x cubed minus 6x squared plus 8x plus 0, I can use long division and divide that by -4x squared plus 12x. Can't use synthetic division here. I've got to go with long division. -4x squared times -2, whoops. Yeah, that's right. -2x is what's going to multiply together. Wait a minute, what am I saying? Let me try to do this like I did in class. -4x squared times something has to equal our target of x cubed. And so I want -1/4 x to make that happen. So -1/4 x. When I multiply -1/4 x times -4x squared, I do get x cubed, which is what I wanted. -1/4 x times +12x looks to me is -3x squared. And when I subtract these two, well, -6 plus 3 is -3x squared. And I can bring these 2 factors down if I need to, which I don't think are necessary in this case, but we'll do that to be consistent. Our next guess has to be -4x squared multiplying by something to equal our new target of -3x squared. The only way that that'll happen is if I multiply by 3/4. -4 times 3/4 will equal -3. The 4's will cancel in the denominator. So we'll type or write plus 3/4. And I don't have to worry about the rest because I've now obtained my linear component of that division. I think there's a slanted asymptote at y equals -1/4 x plus 3/4. So I can now sketch these components. We have a vertical asymptote at x equals 3. We have a slanted asymptote at negative 1/4 x plus 3/4. Now that's kind of hard to draw here, but if that's 3/4, I can drop down 1 and over 4, place another dot, down 1 and over 4 and place another dot. And it kind of looks like we have this slanted asymptote through here. And then see up 4 or up 1 and over 4, up 1 and over 4 would show up here. So there's our slanted asymptote. We have a hole at 0, comma, negative 8/3. So that's what, 2 2/3. There's a hole right here. So with that hole being located here, I tend to believe that the graph is going to curve something like this. It's going to go towards that hole or through that hole. And I just realized we never did calculate our x-intercepts. Our x-intercepts occur when y is equal to 0. So that's only going to be zeros over our denominator. That's when x is equal to 2. So we've got an x-intercept at 2, 0. And we also have an x-intercept at 4, 0. So at 4, 0. So 4, 0 here and 2, 0 here. So I must have done something wrong with my original sketch. I think it was my the calculation for the hole that I messed up on. Oh, this is a 4. There's supposed to be a 4 here. I just noticed that. So let's try that again. When x is 0, we get negative 2 times negative 4. Oops, and that's a positive number anyway. So that's positive 8. And then this down here is negative 4 times negative 3. 8 divided by 12, that's 2/3. So not 8/3, but 2/3. So if we have a hole here at 2/3, that's really close to that slanted asymptote, then the graph is going to tend in this direction. So we're going to hug this slanted asymptote. We're going to go through this 0, through that hole, and race off this way. And this extension of the graph hugs that vertical asymptote, and it turns downward across this slanted asymptote. And that would be a pretty good sketch. So sorry for that misstep there, but I think we're pretty good with what we have right now. I hope that this video helps clarify what happened on test number 5, and I hope the other videos help as well as you prepare for our final exam this semester. Good luck.